has a different quality to it. And so satellites in the way that we have them, I don't think would exist outside of evolution. Another example, just pushing on the laws of physics as they exist now are not sufficient to explain intelligent things that understand the laws of physics and what they can do. It's a very David Deutschian kind of way of thinking about it. Thinking about elements on the periodic table of the elements. There are some that, all the way up to 118 ognesium, which is the highest atomic element that we make in the lab on Earth right now, that are most reliably produced by technology. So if you look at all the physical processes that make the elements, we might have some that were made just after the Big Bang, some are made in the dust of stars, and some are made on planets that have evolved intelligent beings that can control all of the mechanisms and boundary conditions sufficient enough to actually synthesize these elements in high abundance. It's not that they're forbidden by the laws of physics. It's just never going to happen unless you constrain the space sufficiently far to actually produce these elements, which means that you need information to constrain the space to produce them. So the argument I like to make about life is that information, this property that is very abstract and we don't know how to talk about associated to life, and its objects only arise as a product of evolution, learning, and selection. And this is what we call the physics of life. So it's sort of like, in the history of physics, we have discovered new domains of physics by kind of trying to think about things from new perspectives. And one of my favorite unifications in physics was the unification of celestial and terrestrial motion. Right? So before that in human history, no one knew those were governed by the same physics. And now we accept that gravity is a universal physics. It exists everywhere. But there are some objects in our universe, like planets and black holes, where gravity is most intense and is like a really prominent physics that we need to use to study those objects. We don't really care about gravity in the atomic nucleus. Information, I think, is a universal physics, but I think the place where it becomes most relevant is when we study life, because that's where that process is most concentrated. So we are the manifestation of whatever this physics is that we don't understand. Now, this is contrary in many ways to sort of the standard way we talk about things in physics. So I was taught in my physics class about particles in boxes, and also how brains can emerge from particles in boxes with very low probability. Has anybody heard this before, that we might be Boltzmann brains? Do you feel like a Boltzmann brain? I felt one like a minute ago, but I'm not sure now. Yeah. Okay. So the argument is that brains can fluctuate into existence spontaneously, because statistical physics allows it and quantum physics allows it. And I think there's a lot of problems with this argument, for various reasons. One is that we've never observed it happen. So maybe you might want to ask questions about your laws of physics if they make predictions you can't observe. It is interesting cases where people try to use this as cosmological bounds on like properties of the universe and stuff. So I think that they are interesting as a conceptual tool, but I don't think it's a physical argument. And it's interesting how the Boltzmann brain argument has permeated logic of other arguments that people want to make about the nature of life and mind and how they relate to physics. It's not like a culturally isolated phenomenon. It's like people really intrinsically think the universe can generate anything, anywhere for free. And I think that's tantamount to intelligent design, because it basically says the universe has information for every object to spontaneously fluctuate into existence anywhere at any time. Where is all that information? Please tell me. Okay. People want to tell me in the audience I like this. Okay. Got some arguments coming. I'm excited. All right. So where do brains come from? Well, if you deconstruct a brain and look at its past history, brains are products of evolution, right? So they have a long lineage. So this is a very abstract representation of a brain. It's a human brain, but just imagine, like it needs a body. So I'm not saying brains can be disembodied. So I'm just drawing a picture because I like drawing pictures. They're helpful. It's really hard to get the art right though. So minds don't spontaneously fluctuate into existence. They are assembled across time through evolution and selection. So if you think about every step to make a mind, to build a brain, every step takes time. And you can't compress all of that time into an instantaneous, spontaneous fluctuation. A mind is an object that requires time to be constructed. And evolution is the process we know that does that. And so part of the structure of the theory that we're building to explain life talks about objects as being assembled over time. There's a particular way we talk about assembly as a construction process. But the idea being that every evolved object has a structure across time as far as how it is built. So if you start from elementary building blocks, the way we think about it mostly is for molecules right now. So I'm doing a big reach right now by talking about brains, but it's supposed to be a general theory of evolution, and we're working our way toward universal features of the theory. And I have some promising stuff in both labs going on right now. Okay, so if you think about a mind, and you actually look at how you can construct the mind, that is the physical structure of the mind. This is going to be the argument of my whole talk. It's not the instantaneous object of the brain, but the brain is an object that is very large in time. And I'm going to say this over and over again, but this is sort of my conception of evolved objects. They're informational, and you can't see the informational properties because they are ones that have a size in time, not in space. Okay, so this is a mind. Now, I'll explain a little bit more in a few minutes about how we think about how to construct this kind of space. So I'm doing it very conceptually here in a quantitative framework, and as far as the theory that we're building and like the principles of the theory to kind of do like assembly theory 101. But one important feature of this is once you deconstruct an object in this way, you can see that it's been selected out of a very large space of possible objects, right? So if I took a brain apart, and, I wanted to look at its pieces, the molecules that make it, those molecules could be assembled in an exponentially growing space. Every time I add two pieces of a molecule together, every time I form a bond, the size of the space gets exponentially larger. If I get to the size of cells, the space is even larger still. And once I get up to brains and technological civilizations, that space is very large. And it is so large, I don't even think that we can even imagine how big that space is. So remember I said that we can't even estimate how many possible molecules there are with the known periodic table of elements. So a brain actually is very deep as far as it's structured. But then as you're building up this space, you see what a huge space of possibilities that a mind exists in. And in some sense, the brain has carried with it that entire history. It's just rolled up in the present. So it has some capability of understanding the structure of the full space because it's a combinatorial space and it has some remnants of it stuck in the brain. When you look at that combinatorial space, there could be other minds in that space. And here I'm showing two kinds of brains that exist on our planet, which exist in the same combinatorial space and in fact share a lineage up to a certain point in their history before they diverge from each other. So if you look at the causal chains of events of operations or construction processes that assembled our brain, and you looked at the one that assembled an octopus brain, there would be a lot of overlap. We're not that dissimilar. But if I looked at my brain and somebody else's in the room, we're even more similar, which is one of the reasons we can share experiences with each other, is because we're practically the same object when you look at us deep in time. Now, the reason for taking this approach when we're thinking about origins of life, and I also think a lot about alien life, is we need to generalize beyond life as we know it, I think, to understand a lot of the properties of life as an abstract feature of our universe in the sense that we talk about in theoretical physics. So if you think about the sort of paradigm of theoretical physics, like the paradigmatic framework of what is theoretical physics about, it's about building abstractions that unify as many parts of reality as possible under a similar conceptual framing, right? So motion is a good example. I could look at all moving objects and I don't care about their color. I don't care about their shape. I care about their mass and their velocity, right? So what abstractions matter for talking about unifying motion is mass and velocity. And those are inventions of our theories that correspond with measuring devices. What I'm saying here is when we're talking about evolved objects, the abstractions that matter are this kind of depth in time and also its relation to other objects. But I'll talk specifically about concrete observables in a minute. But the reason for doing this is because we don't think necessarily, at least in this day and age, and I hope is the topic of this conference, that the only minds that exist are biological minds, right? I'm not sure that I'm convinced any AI right now is a mind, but other people might be. But we do care about technological minds and we care about alien minds, right? What is the space of possible minds our universe can construct? I think this is a really relevant question and an interesting question for reframing some of the ways that we talk about the nature of mind. And obviously that's an important, very pressing conversation that people are having now. So when we think about where we exist in the space of possibilities and how we interact with the world, and that other things have co-evolved with us on the same planet, there's a whole bunch of trajectories through this space that we don't know. And those are, maybe technological minds that might be evolved from our same chain of event, our same causal chain constructed over time, or they might be alien minds that have completely different histories than we do. So I've been putting on this axis here assembly time because I'm not really actually thinking about this as clock time. I think about time in a different way than standard conceptions of physics. It's much more like a causal time. And it's always interesting to me to look back at the history of physics trying to invent new physics because you see that like every theory of physics invents its own concept of time. So why not? Actually, it's interesting because every century invents a concept of time, and they're really strongly correlated with the cultural narratives of that period in time and technological inventions. Yeah, I'm actually more thinking about like Clockwork Universe, and like Newtonian time is invented based on clocks, right? So what is causal time? I think it's because we live in a very complex world and we're realizing time is not exactly linear. It's combinatorial, which is fun. Okay, so I mentioned at the beginning this assembly theory. So assembly theory is a theory that is structured to solve the problem of the origin of life, which I'll talk a little bit how we're thinking about that in a minute. But the way that is like sort of the base of assembly theory is to say that there are objects you observe, right? Those objects we observe are physical things that exist like you and me. And you can deconstruct those objects to their basic building blocks. So let's not talk about you and me because it's too complicated, but let's talk about a molecule. A molecule is made out of bonds, right? So people think it's made out of atoms, but if you're actually talking about constructing a molecule is made out of bonds. So bonds are the physical thing that build molecules. Molecules made out of bonds. So if I take a molecule apart and I look at its bonds, there's a whole space of molecules I could build, that combinatorial space of chemistry I was talking about, and it's exponentially large. And in fact, if I had no physical constraints, that space is super exponentially growing with every new operation I do in that space. So that space is huge. That space is actually non-physical because I haven't imposed any of the laws of physics or operations we know that can happen in our real universe. So we might want to add some constraints and say we only want to do possible operations. We only want to make bonds that actually can form. So Lego is maybe even better. So some of you are not chemists. I see people scratching their heads like thinking about how would you construct a human and how would you construct a molecule. How many people have played with Lego? Lego. Okay, we know Lego. Okay. You know how they have little pieces on them? So, like what are the knobs called? I don't know. Studs. Let's just call them studs. Okay, so they have little studs on them, right? So assembly, the space of possible Lego structures, if there were no physics involved, no constraints imposed by how they have to fit together, let's say you have super glue, is like a really huge space, right? You can make all kinds of weird stuff out of Lego. And every time you add a new piece, the number of possibilities grows. If I am constraining myself to actually using those little studs to piece things together, I've constrained the space of possible objects to be ones that are physically consistent with the rules of Lego universe. And then the next sort of constraint you might want to add is that you can't spontaneously assemble things for free. You have to build them out of things you built already. And this is what we call assembly clause or assembly contingent. This is an old label, so it's actually called assembly contingent in the paper, but that's this one. So you've added more constraints. And this is the feature that objects are built along historically contingent trajectories, which means if I want to build a Lego castle, I build a part of it first, and then I add that part to another part, and then I add that part to another part. And so this actually constrains the sort of trajectories through what objects get built, because once you start constraining and building things, you can only build out of what you built before. And so this means that the sort of trajectories for building objects are historically contingent. So what we see when we take objects that exist and we deconstruct them is a particular example of a contingent history, but it tells us something about the space of histories that could have been, that sort of space around it of what evolution could have done but didn't. And so assembly theory doesn't have initial conditions. It doesn't have laws of motion. It has objects and their causal histories and then constraining the future based on the causation that you find in objects in the present. Now, this gets at some interesting things because what you talk about as fundamental in this theory is not what we talk about as fundamental in current theories of physics. And one of the reasons for that I think is really important because, again, looking at the history of science, We have invented a lot of technology in the short history of science. And every time we invent new technologies, what we call fundamental changes. A good example is atoms, right? So atoms are the things in the periodic table, and they're called atoms because we thought they were indivisible, like the Greek atom. And then we realized they had substructure. And now sort of the most fundamental theories that people want to propose are things like string theory, which is even more fundamental, but currently inaccessible to our technology. We want to define fundamental as the smallest objects in the universe. The problem is, when you're an observer existing in the universe, what you call fundamental changes with your evolutionary history, how much technology you've evolved, how much you can measure. And so a theory of evolution that tells you about where you are in an evolutionary chain cannot have a fixed, finite object as an indivisible object as your fundamental particle. It can't be the fundamental structure of your theory. So assembly theory is a theory of objects. It's kind of funny because I got through a whole physics education without knowing what an object was. And then I started to think about it. And so we define objects as having several features. One is that they're finite and distinguishable. So you see a basketball and a soccer ball in the universe. You don't see a smear of every possible kind of configuration of ball in between. They're finite, distinguishable objects. Objects are breakable. I could decompose your brain into atoms. I can decompose a molecule into atoms. I cannot decompose an electron into anything. It is not an object. It's a limit of your observations. Objects exist more than once. This is a weird feature and probably one of the most unintuitive things, but one of the key features of assembly theory is this idea of copy number, that things that are created by evolution can be produced again. And that the copies of objects matter. So we are not identical objects as humans. So you say, like, I'm not an object in the theory, I don't exist. But actually, if you look at us and you look at our causal history and you look at where we exist in the space of possible, we're nearly identical. You know, we're 1% of our genome is different, right? So you can follow these causal trees building up these objects all the way to the branches, and we're the things that are alive now are just the branches of these trees. Objects are lineages. So this gets to the point about objects existing in time, right? So in order to get to something like you or I, we think, about 4 billion years of evolution has to happen on a planet. And my friend Michael Lockman is really great about saying, when you ask him how old he is, that he's 3.8 billion years old, because some of the information in his body is that old. And even in your lifetime, you're not the same atoms you were when you were born. So what is you? You are the lineage. You are the thing that keeps getting reconstructed.